This kind of discovery only shows up when people stop looking at the sky like it is just lights and dots and start treating it like a real place driven by chemistry and cause and effect. The James Webb Telescope aimed its mirror at 3I Atlas and did exactly what it was designed to do: break faint light into an ultra-detailed spectrum. The level of precision is intense, almost like reading a barcode written directly by molecules across the surface. 3I Atlas is still a fast-moving outsider, a small object cutting through the solar system on a one-way path with no intention of staying. But what Webb extracted from that light immediately shifted the conversation. The data lines up with complex carbon-bearing compounds and a mix of gases that, under the right conditions, land in the same category scientists associate with potential biosignatures. This is not proof, and it is not a declaration of life, but it is a possibility, and that alone was enough to make researchers slow down, look again, and take the signal seriously instead of brushing it aside. Calling it 3I Atlas by its full name actually matters. The 3I quietly signals an interstellar origin, meaning this object did not form around our Sun. Atlas refers to the survey system that detected the motion early and alerted the scientific community before it slipped past unnoticed. This is not another comet from the Oort cloud or a routine asteroid from the main belt. It is material from a completely different planetary system, ejected by gravitational chaos, drifting for ages before passing through our neighborhood. That alone makes it valuable. What changes everything is the chemistry, which looks less like sterile rock and more like an active, complex inventory that overlaps with what life tends to use and produce. Webb's real advantage is its ability to catch the cold, faint signals that ground-based telescopes usually miss, especially in the near and mid-infrared range. Every molecule leaves a signature, soaking up and releasing energy at very specific wavelengths. Those tiny dips and bumps in the data can be matched straight to lab results, turning light into a chemical readout. When 3I Atlas was still far out, it was barely glowing at all. Back then, the activity was muted and easy to overlook. But as it moves closer to the Sun, everything changes. Heat starts pushing volatile ices into gas, dust lifts off the surface, and a coma begins to form or thicken. What was once quiet turns into a moving chemistry experiment, warming up in real time as it travels. That setup plays perfectly to Webb's strengths because the gases spilling into space effectively announce what the object is made of. Even if the nucleus itself stays unresolved and tiny, possible signs of life do not mean there are organisms hitching a ride on a dirty snowball like passengers on a train. The idea is narrower, but still shocking. It points to chemistry that sits far from equilibrium, a state that is difficult to maintain without something actively replenishing it. In planetary atmospheres, certain gas combinations can imply ongoing processes that resemble biology. In comet-like objects, the logic gets messier. Sunlight, radiation, and mineral reactions can also create strange compounds. Still, when researchers spot an unexpected mix, especially reduced and oxidized species appearing together or complex organics showing up in large amounts, the question becomes impossible to ignore. If this object really formed around another star, then its chemistry is a direct sample from that system. If it even hints at biochemistry, it suggests that pathways toward life may not be rare, and the timing only adds pressure. 3. I-Atlas is getting closer, which means every new observation should be sharper than the last. Closer usually means brighter, and brighter means more signal, with less room for guessing. But it also means the object starts sliding across the sky faster, which makes tracking a lot tougher. That is where Webb's precision matters. With tight planning, it can lock onto fast-moving targets and stay steady. Every new observation window becomes another chance to see if a suspected signal is real or just noise playing tricks. If a specific absorption line grows stronger as outgassing increases, that supports the detection. If it fades, shifts, or disappears when the viewing angle changes, that can point to contamination, mislabeling, or a short-lived chemical process. The approach phase turns this into a series of stress tests instead of one dramatic snapshot meant to grab headlines. The most interesting part of all this is not the phrase people love to repeat, signs of life. It is the pressure this puts on scientists to be clear about what actually counts as convincing evidence. Spectra are messy by nature. Dust adds a thermal glow that can drown out weaker features. Water vapor and carbon dioxide often dominate the signal and make everything else harder to separate. Instrument quirks can also fake faint lines if calibration is sloppy. Then comes the bigger question of origin. Is the gas coming straight from ancient ices that formed with the object, or is it being cooked on the surface by radiation chemistry? It could even be trapped in clathrates, sealed away until heat cracks them open and lets everything spill out. Each explanation points to a very different story. Webb's data can narrow down temperatures, dust behavior, grain sizes, and gas ratios, but the meaning still depends on careful modeling. The excitement is real, but moving from intriguing to convincing takes discipline and skepticism. What makes 3I Atlas especially dangerous as a target is that it is not a distant exoplanet. Those are just pixels. This thing is inside our solar system right now, a real laboratory passing through. Even without a spacecraft, every major telescope can get involved. Ground-based observatories can capture visible spectra, polarization, and detailed gas lines. Under the right conditions, radar could even hint at its size and shape. Other space telescopes can step in and cover complementary wavelengths, and that is how uncertainty gets squeezed out. You stack independent measurements until the explanation either falls apart or locks into place. With 3I Atlas getting closer, what started as a single intriguing dataset is turning into a full multi-instrument campaign, where every result cross-checks the next and pressure keeps building. The implications spread in several directions at once. For astrobiology, the biggest shift may not even be technical, but psychological. For decades, the search for life has meant staring outward, trying to decode the atmospheres of distant planets light years away. An interstellar visitor flips that logic. Instead of reaching across space, material from another system comes to us. No futuristic rocket required. If complex organic chemistry turns out to be common in these visitors, it strengthens the argument that prebiotic ingredients are everywhere. If the chemistry looks even more organized with patterns that hint at biological processing, it pushes the idea that life-related chemistry might survive in environments far rougher than a calm, Earth-like planet. Even a clear null result would matter. It would define what raw interstellar building blocks actually look like, which feeds directly back into how scientists interpret exoplanet spectra. 3I Atlas is a reminder that the solar system is not sealed off. Interstellar objects are not just oddities, they are proof that planetary systems trade debris. If one system can eject comets and asteroids, those bodies can wander for ages and occasionally pass through others. That reshapes how panspermia is discussed, not as science fiction, but as probability. The real question becomes whether ejection forces, radiation exposure, and long travel times leave anything intact. Webb cannot answer that outright, but it can tell us whether the ingredients and protective structures exist. A porous, ice-rich body with deep layers could shield complex molecules for immense spans of time. A dry, fractured rock likely could not. The spectrum, combined with motion and thermal modeling, narrows down exactly what kind of traveler this is as it keeps getting closer. This situation also carries a practical edge that people cannot ignore. Whenever something from deep space moves into the inner solar system, questions about risk come up fast. An interstellar object on a hyperbolic path is not coming back, and its speed is usually extreme, which would complicate any theoretical deflection effort. That said, most of these visitors are small, And the sheer scale of space makes the odds of impact incredibly low. The real takeaway is observational, not apocalyptic. Getting closer means more chances to study it, but it also creates urgency because the window does not stay open for long. This turns into sprint science. Telescope schedules, fast data processing, analysis pipelines, and coordination between teams suddenly matter just as much as the physics itself. If the reported biosignature-like features involve molecules that, on Earth, are strongly tied to biology, the conversation immediately shifts to false positives. A molecule can be produced by life without being exclusive to life. Many organic compounds form naturally in cold interstellar clouds on dust grains, and comets are already known to carry chemistry far richer than anyone expected. Radiation alone can push reactions toward complexity without biology. Shock heating during ejection from the original system could also create strange mixtures. Another possibility is that the object passed close to an active body long ago and picked up material, turning its surface into a patchwork rather than a clean sample. Each of these explanations is compelling on its own. The key point is that even if the life angle falls apart, the object still shows how complex chemistry can emerge in deep space. What Webb can do, especially as 3I Atlas continues to brighten, is measure molecular ratios and isotopes with growing confidence. Isotopic ratios, like differences in carbon or oxygen isotopes, act as fingerprints of where material formed. Different stellar nurseries leave different signatures. If those ratios look clearly unlike anything seen in typical solar system comets, it strengthens the interstellar case beyond orbital math alone. Unusually high levels of certain molecules compared to water could signal a different chemical heritage or thermal history. As it moves closer to the Sun, layering may even reveal itself. Early outgassing could release the most volatile ices, while later heating exposes deeper reservoirs hidden for ages. Watching the spectrum change over time is like watching pages turn in a book, except the pages are made of gas instead of paper. As different molecules rise and fall, the story slowly reveals itself. There is also an emotional weight here that is hard to strip away from the science. For a long time, people imagined evidence of life arriving as a radio signal or a clean atmospheric signature from a distant planet. An interstellar object brings a different kind of tension. If evidence exists, it is not far away. It is physically passing through our neighborhood. That closeness shifts the way people talk about it and react to it. There will be a strong pull to treat it like a visitor with intent, to assign meaning where there may only be physics. Scientists will have to stay disciplined with language while still explaining why certain chemistry actually matters. The public will also have to relearn something important. Extraordinary claims do not arrive as single dramatic moments. They emerge through chains of evidence that either survive repeated testing or fall apart under pressure. If the signals really are suggestive, they will need time and scrutiny to hold up. One immediate ripple effect is renewed pressure to talk about interception missions. The technical challenge is brutal. Interstellar objects move fast and give very little warning. Still, every detection adds motivation to build rapid response capability. That could mean small, agile spacecraft that launch quickly, or interceptors positioned in advance and redirected when needed. Even discussing those options reshapes priorities. It forces space agencies to ask whether sampling a visitor from another star is worth long-term investment. The fact that 3I Atlas is getting closer makes that question feel less theoretical and more urgent, because reachability depends heavily on timing. The implications also stretch into how life itself is framed. If small bodies can carry chemistry linked to biology, then biosignatures may not live only in atmospheres. They could appear in ejecta, plumes, debris, or brief comet-like events, widening the search while making interpretation harder. That means future detections of molecules tied to biology may be less clear-cut than hoped. At the same time, it opens the door to richer comparisons and deeper context across very different environments. Interstellar objects could end up becoming reference points for non-biological complex chemistry, giving scientists a baseline for what nature can build on its own before life ever enters the picture. Either way, 3I Atlas getting closer is what drives this entire moment. Every day of approach creates another opportunity to sharpen the spectrum, stress test alternative explanations, and watch how the object reacts as sunlight digs in. This is not a single announcement frozen in time. It is a moving target that forces science to move alongside it. Webb's initial glimpse, whatever it ultimately turns out to represent, already changes the kinds of questions being asked. The search for life stops being a distant, patient stare and starts looking more like a pursuit unfolding across the solar system. With chemistry as the trail and time as the limiting factor, the implications are already tangible, even while certainty remains out of reach. We are no longer guessing what material from another star system might look like. We are actively measuring it as it passes through our neighborhood. The focus now shifts away from the rush of a surprising signal and toward the slower craft of turning that signal into a physical narrative. The wavelengths Webb isolates are not just molecule labels. They carry information about temperature, density, and where the light originates within the expanding cloud. A feature can appear strong for different reasons. There may be a large amount of the molecule, or it may be positioned perfectly to absorb or emit at that moment. Dust can also shape the background glow in ways that exaggerate certain signals. That is why interpretation becomes almost forensic. Researchers start asking whether gas is escaping evenly or erupting in bursts from cracks and jets. They look at whether dust grains are fluffy or compact, whether the coma is dominated by tiny efficient emitters or larger particles that behave more like soot. One of the clearest clues as 3I Atlas keeps moving inward is how fast its activity changes. Objects rich in highly volatile ices can switch on early and aggressively. More processed bodies may stay quiet until heat penetrates deeper. The pace matters because it reveals structure beneath the surface. If the coma suddenly ramps up, it points to pockets of material that stayed sealed until heat cracked them open all at once. If activity rises slowly, it suggests a more even surface or a layered release happening step by step. That distinction matters when interpreting life-adjacent chemistry. A sudden plume can exaggerate a small, unusual reservoir, while steady outgassing is more likely to reflect what most of the object is actually made of. Tracking those changes is like figuring out whether you are tasting the whole soup or just hitting a clump of spice at the bottom of the pot. Dust is the wild card that makes this harder and more interesting at the same time. Dust grains carry organics, metals, and minerals, and they can either imitate molecular signals or bury them in infrared noise. Some silicates create broad features that wash across the spectrum. Carbon-rich grains can produce smooth slopes that hide weaker gas lines entirely. If dust grains are coated in complex organics, they can even show features that resemble specific molecules, despite the gas phase telling a different story. At the same time, dust adds crucial context. Mineral makeup can hint at formation temperatures, processing history, and whether the material looks familiar compared to known solar system comets, or whether it looks like something built under completely different conditions. If the grains appear unusually carbon-heavy or show unexpected crystalline structures, the narrative shifts. It stops being a typical icy drifter with a strange detail and starts looking like a fundamentally different recipe. Observation geometry also becomes part of the puzzle. As the object moves, the angles between the sun, the object, and the observer change how energy is pumped into the coma. Some spectral lines brighten simply because illumination improves, not because more material is present. Certain molecules fluoresce in ways that depend on sunlight intensity at very specific wavelengths. If those effects are ignored, illumination can be mistaken for chemistry. That is why teams build linked models that connect orbit to light, light to gas, and gas back to the nucleus. It is a chain, and any weak link can distort the story. When the chain holds, the payoff is bigger than a list of compounds. It becomes a working picture of how an alien object behaves under our sun. What makes the idea of possible signs so fragile is that biology is not just one chemical ingredient you can point at. On Earth, life acts like an organizing force. It does not only create molecules, it shapes environments into patterns that stick around, even when chemistry alone should wipe them out. So the sharper way to frame Webb's hint is not asking whether it spotted a life molecule, but whether it picked up on a pattern that feels too organized for the environment it is in. Inside a small body's coma, organized behavior could show up as strange ratios that stay stable even as activity changes. It could look like pairs of molecules rising and falling together, suggesting a shared source rather than random surface reactions. It might also appear as complex chemistry showing up consistently without the expected precursor molecules appearing in matching amounts. The tension comes from the uncomfortable truth that non-living chemistry can also look organized. Hidden constraints like trapped gases, layered ice structures, or selective release from different depths can produce patterns that mimic intention. Because this material is interstellar, laboratory work suddenly becomes frontline science instead of background support. There are massive databases of molecular spectra, but they are not endless, and they are not always complete for the exact temperatures, pressures, and mixtures involved here. A faint feature can often match more than one candidate. The difference may come down to subtle line shapes or nearby bands that are easy to misread. That is when chemists and physicists step in and recreate the conditions directly. They chill materials in cryogenic chambers, shine simulated sunlight, bombard ices with particles, and measure what comes off. If a proposed molecule seems exciting but the lab spectrum does not line up, it gets pushed down the list. If the lab data clicks cleanly into place, confidence rises. This back and forth between telescope and laboratory is one of the most powerful parts of the whole process. A distant observation can suddenly drive experimental chemistry on Earth. As scientists refine how to read the molecular language of space, statistical discipline becomes just as important as chemistry itself. When a signal sits right at the edge of detectability, it is easy to fall in love with the most dramatic explanation. The correct move is colder. Teams ask how often similar features appear when the same analysis is run on blank sky or on objects where no such signal is expected. That kind of control work sounds dull, but it is what turns an eyebrow-raising idea into a result that can survive pressure. In practice, it means teams challenge each other's pipelines, reprocess the same data with different assumptions, and hunt for the same features using completely independent methods. The implications stretch far beyond this single object if the scientific community gets sharper at handling uncertainty and untangling messy spectra. Every future claim about habitability or biosignatures stands to gain from that discipline. There is also a quieter but deeper shift happening in how life-related signals are defined in the first place. Earth-based thinking has always been our strongest reference point, but it is also a built-in constraint. Certain molecules feel biologically suggestive because they are common products of life on Earth or tightly woven into our own biochemistry. But a completely different biosphere might run on different solvents, different energy systems, or entirely different molecular frameworks. In that sense, 3I Atlas becomes a stress test for imagination. If its chemistry looks strange in ways that do not line up neatly with Earth, it forces researchers to rethink what counts as plausible biology. That pressure expands the catalog of life-adjacent chemistry. If the chemistry looks oddly familiar, it raises another possibility. Certain molecular strategies may be convergent. Different forms of life, emerging independently, could land on similar solutions simply because physics and chemistry reward efficiency. The closer approach also opens the door to detecting time-based patterns tied to rotation. Even if the nucleus itself never resolves into a visible shape, gas and dust release can pulse with a spin period. Active regions rotating in and out of sunlight can imprint rhythms into the data. That kind of modulation is valuable because it reveals structure without needing an image. Those patterns can show whether activity comes from isolated vents or from a more evenly active surface. They can link specific molecules to specific regions, hinting at separate reservoirs beneath the surface. In some cases, they may even point to surface diversity, where one side is richer in certain compounds due to an ancient collision or uneven deposition in its original system. Instead of a static list of ingredients, the object starts to feel dimensional. It is closer to hearing an instrument and inferring its shape from shifting harmonics. Dynamics add another layer of insight that does not depend on chemistry alone. Outgassing can act like tiny thrusters, nudging the trajectory in ways gravity alone would not predict. Measuring those deviations helps constrain how strong the activity really is and whether it is directional. Focused outgassing suggests jets and localized sources, more even release points to a broadly active surface. Either way, it offers an independent check on how much material is actually leaving the object. All of this feeds back into figuring out how much of each molecule is actually there. It also helps pin down what kind of body this really is on a mechanical level. Is it a fragile pile of loosely bound material that sheds easily, or a tougher nucleus that only vents through a few narrow openings? That mechanical character matters because it controls how well interior material could have stayed protected during long interstellar travel. The ripple effects do not stop at physics. Communication and culture get pulled into it too. This is the kind of discovery that forces a public reckoning with what evidence actually means. When people hear phrases like possible signs of life and assume certainty, later debate can sound like backtracking. But if the story is framed as a layered investigation, where chemistry points to hypotheses that must earn their credibility step by step, the public sees science as a living process instead of a machine that spits out answers. That distinction matters because the search for life carries extra emotional weight. It is not just another measurement on a chart. It touches belief systems, philosophy, and the deep human urge to not feel alone. How this moment is explained can either strengthen trust in scientific methods or feed suspicion if the nuance gets lost. There is also a quieter implication that does not depend on finding biology at all. Interstellar visitors show that planetary systems are not sealed-off projects. They are messy, leaky, and dynamic. Material gets thrown out, wanders, and sometimes crosses into other systems. That means the raw ingredients for planets, and possibly for life, are not only common but mobile, traded across stellar neighborhoods over immense timescales. Even if life itself turns out to be rare, the chemistry that makes life possible may be widely mixed. That shifts the perspective from life requiring a perfect local setup to life emerging within a universe already stocked with complex material. It reframes the problem from scarcity to organization. On the technical side, every new observation window also offers a chance to untangle overlapping molecular signals. By studying multiple wavelength regions that respond differently to the same species, researchers can separate what is blended and sharpen what is real. Some molecules hit hard in one wavelength region and barely whisper in another. Catching both is like checking an ID with more than one document. That double confirmation matters even more for complicated organics, where a single spectral feature can pretend to be several different candidates as the object brightens. As 3i Atlas gets closer, those secondary checks move from wishful thinking to something you can actually pull off. At the same time, measuring the thermal continuum matters just as much. The smooth glow from dust and the warmer nucleus sets the baseline that keeps gas features from being overhyped. It sounds like boring accounting work, but when the headline feels explosive, bookkeeping is what keeps the whole result from falling apart under its own weight. This moment also highlights why coordination between different observatories matters for physics, not bragging rights. Different wavelengths look at different parts of the coma. Some measurements are tuned to parent molecules coming straight from the nucleus. Others mostly see daughter species that form when sunlight breaks those molecules apart after release. That separation is critical if you want to know what is actually stored inside the object rather than what gets cooked up after exposure. If a molecule mainly shows up as a photochemical byproduct, it still tells a story, but it points to a very different origin than a molecule vented intact. Getting that distinction right changes the claim from this object contains X to this object produces X under solar radiation. Those are not the same statement, and they carry very different weight when biology enters the conversation. There is also a quieter lesson here about contamination and purity. When scientists study meteorites or comet dust returned to Earth, they obsess over avoiding terrestrial contamination because even tiny traces can wreck the interpretation. With remote observations, the contamination threat shifts. Instead of microbes, the risk comes from photons, detector quirks, and poorly modeled backgrounds. It moves from dirty lab tools to subtle instrumental artifacts. In a way, this event is pushing the field to treat remote biosignature-style claims with a sample return mindset. Document everything, measure every uncertainty, and assume the most exciting explanation is wrong until it survives every possible challenge. That cultural posture becomes an implication on its own because it quietly raises the bar for every future announcement. Another layer of intrigue comes from how sunlight and vacuum work together as something closer to a chemical sculptor than a simple heat source as 3I Atlas moves inward. The surface is not just warming up, it is being stressed, flexed, and pushed toward change. Small temperature swings between lit and shadowed regions can crack brittle surface layers, exposing material that may have been sealed off for unimaginable lengths of time. When that happens, the coma stops being a reflection of surface leftovers and starts acting like a window into deeper chemistry. What escapes is no longer just residue, it is history. If Webb keeps tracking those transitions, it has a chance to catch moments where the object effectively refreshes itself. A weathered outer skin can give way to newly exposed layers, shifting which molecules dominate the signal. That is where an important distinction shows up between an object that formed quietly and one that lived a rough life. A small body kicked out of another system may have been yanked around by giant planets, scorched during close stellar passes, or battered by collisions long before it ever drifted into interstellar space. Those events can cook some regions, preserve others, and leave behind a chemical patchwork that only reveals itself once sunlight starts activating it in stages. If the spectral signatures change in a way that looks like switching between distinct chemical regimes rather than smoothly scaling upward, that patchwork idea starts to hold weight. A patchwork can also fool you if you only observe one phase, which is exactly why continued monitoring matters so much. There is also a quieter possibility hiding in the coma itself. Some molecules may not be released directly at all. They could form after release as gases react with sunlight-driven fragments in a dense environment. Chemistry in space can move faster than expected, especially once ions appear and electromagnetic forces begin steering reactions in subtle but meaningful ways. If that happens, the coma briefly turns into a short-lived chemical reactor, producing outputs that can look more complex than the original ingredients. Webb's time-resolved sensitivity helps separate what is released immediately from what forms later by tracking which spectral features lag behind shifts in overall activity. Even a small delay matters because it tells you whether the object arrived carrying complexity or whether it is generating it on the fly as sunlight reshapes the chemistry. All of this funnels into one central implication. The closer 3I Atlas gets, the more it stops being a single mysterious data point and starts behaving like a system. And behavior is what turns a headline into understanding. A frozen snapshot can be argued forever. a spectrum that responds consistently to heating, rotation, and bursts of activity, begins to lock the story into place. Once patterns repeat across changing conditions, the explanation space shrinks, whether people are comfortable with it or not. If the chemistry keeps pointing in the same provocative direction, it becomes harder to dismiss as coincidence. And if it does not, the reasons why still matter just as much. Either outcome teaches us something real about how complex molecules survive, break apart, and transform during long journeys through interstellar space. That is where the real value of this moment sits. Not in a single claim, but in watching a foreign object reveal how it behaves under our sun. What we are seeing is not just data, but process, and process is where understanding lives. If you enjoyed this breakdown, drop your thoughts in the comments and let us know what you think about the possible life-related chemistry tied to 3I Atlas. Make sure to like the video, subscribe to the StellarDrift channel, and share this with anyone who is following the story. We will see you in the next one.